Solidification is the name of the process by which a liquid, in this case a metal, transforms into a solid. From everyday observation, we see that it doesn't happen instantaneously. Why not? Thermodynamics explains that the solid phase has a lower free energy than the liquid phase at temperatures below the metal's melting point. This means that we expect to observe a solid, because that's the more stable phase. However, liquid gallium has been observed at temperatures of 150 Kelvin, when its melting point is 300 Kelvin. There must be some type of energy barrier that must be overcome, and some time-dependent process that occurs during this transformation. There are three pathways along which this transformation can occur: homogeneous nucleation, heterogeneous nucleation, and metallic glass formation, or vitrification. I'll begin with homogeneous nucleation, which describes the growth of a nucleus of the solid phase suspended in the liquid phase. Then I'll move to heterogeneous nucleation, which involves the same process, except that the nucleus forms at an impurity in the melt, either a foreign particle or a mold wall, for instance. Finally, I'll discuss vitrification in metals, which presents an alternative to the nucleation and growth processes of the first two. To begin the discussion on homogeneous nucleation, consider two equal volumes at some fixed temperature below the melting point of the metal. One is 100% liquid and has a free energy given as the free energy per unit volume of the liquid times the total volume in the system. The other volume has a nucleus of solid within that liquid. Its free energy is given by the volume of the sphere times the free energy per unit volume of the solid, plus the free energy of the liquid times its volume, plus an interfacial energy consisting of the surface area times the interfacial free energy per unit area of that surface. To make later calculations easier to follow, the liquid volume in the first box is broken into two components to match the two components in the second box. The change in free energy between these two systems is equal to the energy of the second minus the energy of the first, which reduces to the volume of the sphere times the difference in free energy per unit volume of that sphere, plus the surface area times the interfacial surface energy. That difference in energy per unit volume is given by the latent heat of fusion times the amount of undercooling divided by the melting temperature. The change in free energy as a function of the radius can be written out by substituting the formulas for volume and surface area of a sphere. Let's take a look at the graph of that function. Plotting the energy terms on one graph reveals a maximum in the free energy difference occurring at a specific radius, here on the figure. This means that there is some critical size that must be reached before the nucleus becomes stable and grows. Smaller than that size, the system's free energy is reduced if the particle shrinks, so the particle will shrink. If we look at the equations of the critical radius and the free energy, which were determined through differentiation, we see that both decrease with increasing undercooling, as the undercooling is in the denominator of these equations. This means that for a given melt, as the temperature decreases, the energy required to create a nucleus decreases, so it becomes easier to nucleate at lower temperatures. Now, up to this point, the assumption has been made that the nucleus is a sphere with a homogeneous interfacial free energy. Because this nucleus is made up of atoms, its shape will not be a perfect sphere, and its interfacial energy can change depending on how the atoms pack together to form that nucleus. While the most stable structure is often a close-packed face-centered cubic structure, a metastable body-centered cubic phase with a lower interfacial energy has been postulated. Swope and Anderson's simulations using Lennard-Jones potential interactions of a large number of particles showed that indeed there is a free energy barrier for homogeneous nucleation. They also determined that the critical cluster size to be between 10 and 20 close-packed atoms. Their analysis showed evidence of a metastable BCC phase, which has been confirmed in simulation and experiment to have a lower free energy barrier. There have been discrepancies as to whether or not this BCC to FCC transition occurs. Swope and Anderson's simulations showed weak evidence of the transition, but other simulations have showed strong evidence for it. Experimental data has been difficult to obtain, as explained by Oxtoby, because necessary purity to observe homogeneous nucleation is very difficult to achieve. However, advances in containerless solidification experiments, such as those by Loser, show that a metastable to stable transition in fact does occur. Now we'll take a look at heterogeneous nucleation. Earlier, the particle formed in the center of the liquid volume. What would happen if this nucleation occurs at the mold wall of the melt instead? Here's a close-up of that nucleus. Equating interfacial tension vectors for the mold-liquid, solid-mold, and solid-liquid interfaces yields a function dependent on the wetting angle, theta, which describes the shape of the particle on the wall. That particle's free energy can be described just like the spheres earlier, but with the addition of the new interfacial energy terms. Because the solid mold interface grows at the expense of the liquid mold interface, the latter energy term is subtracted in this equation. That function can be simplified to the following equation, which is recognized as the homogeneous free energy times the shape function of that wetting angle. Because that factor has a value equal to or less than 1, the heterogeneous nucleation energy will always be equal to or lower than that for homogeneous nucleation. If we look at the two curves as a function of radius, we see that the critical radius occurs at the same point, but the free energy is lower. Recalling that these equations use a cubic dependence on radius from the volumetric term, and only a quadratic dependence on from the surface energy term, we can see why interfacial energies play an important role in the nucleation process for a small particle. As the nucleus grows, the volumetric term drives the free energy. That growth occurs because an atom diffuses across an interface from the liquid to the solid. Diffusion is governed by many factors, but one of the most important is temperature. As the temperature decreases, diffusion rates decrease. So, as the temperature decreases, there will be more nuclei forming, but they will grow more slowly. The second important factor in diffusion is time. It takes a finite amount of time for an atom to diffuse across the interface from the liquid to the solid. So what would happen if we cooled the melt so fast that the atoms couldn't jump, and therefore couldn't nucleate? Instead of nucleation, the system will undergo vitrification. Vitrification, in general, is considered to be an increase in viscosity from the liquid phase to the solid phase. Once the viscosity of the cooling liquid reaches a certain point, it is considered a glass. Essentially, the atoms in the liquid slow down to the point where their configuration is stable, but there are energy barriers preventing it from transforming to its most stable state. This means that formation of a glass must be achieved by avoiding crystallization. To do this, the cooling from a liquid, where the atoms are moving too fast to stay in a nucleus-like arrangement, to a glass, where the atoms are configurationally frozen, must occur very rapidly. This is difficult with a pure liquid metal, which is a very low viscosity as it solidifies. But a deep eutectic point helps achieve this transition by eliminating the solid-liquid phase field. Thus, the temperature range over which the liquid atoms must slow down is very small, and a high cooling rate can be applied to lock in the positions of the liquid atoms before they crystallize. This process results in an amorphous structure. Johnson discusses an alternative way to assist this glass transition, and that is chemical frustration of the lattice. By introducing more and more atomic species to the system, the necessary ordering for crystallization becomes more and more difficult to achieve, which makes vitrification a more viable option. Indeed, vitrolloy, one of the first highly commercialized metallic glasses, uses such a process. Because crystallization involves diffusion, which is rather slow at temperatures below the glass transition, the amorphous structure cannot transform into the more stable crystalline structure. This discussion has led to there being two different structures for a metal cooled from a melt. There's the usual crystalline structure, with grains of close packed atoms and the amorphous structure of a metallic glass.